All right, Clement. So now we're back for round two.
Hey Dan, yeah, thanks for having me again.
Oh, thanks for coming back. I mean, we had a great discussion last time about your work about machine learning and probability and statistical physics, and there were a bunch of philosophical issues that came up in that discussion. And well, we talked some more, and I guess we're both willing to talk about these philosophical issues. Is
Yeah,
that right?
Well, yeah, go for it.
Oh, okay. So some of the things. So looking over what we were talking about last time. Here are a couple of things that came up. You posed this question: why is the world learnable?
That's right.
Right. When we were talking about machine learning, or really, why are some things learnable and some things aren't?
Yeah.
That's one thing. So that led to a discussion about there was some difference between the way we talk about some math, things from math, abstract mathematical entities, and the things from physics or the things from experience. That's a very old problem. Something else, I don't know if you call this philosophy, but we returned to this a couple of times, are the complex numbers real or necessary? What are they really for? Do we really need them? Or are they just some invention? That was something that came up a couple of times in the discussion. And then at the end, there was this issue, I think you brought up, what math would aliens know?
Yeah, that's an amazing question. I mean, I love it at least, yeah.
You love that? Okay, so I mean, I happen to think that actually these questions are related. They involve some related ideas that maybe we can get into. So let's just see what normally I would make a whole lot of prefatory comments talking about philosophical things, with lots of caveats and whatnot. And I hope we don't damage our reputations too much talking about some speculative stuff. But if we hold ourselves to some scrutiny, let's just see if we have any insight into any of these things. So let me put you to that question, since you like it so much. What do you think? How do you approach this question? What do you think aliens? What are you talking about? What would they know when we talk about math?
Well, I mean, okay, so we of course are making some kind of mental models of what aliens should be, and I mean, maybe something that crosses my mind right now, and maybe a hypothetical question that, yeah, would make it a little bit more focused. It's imagine that 3 million years ago, when man came to be, some aliens actually took some of the people on our planet and put them on another planet. And imagine, a civilization would have developed maybe completely independently from ours. Maybe they would still speak, but they wouldn't look like us, but it would just be a completely different civilization. And of course, I think that it's reasonable to expect that, starting from where we were 3 million years ago, we would, mankind would somehow evolve to eventually become quite developed, and people building buildings and things like that. Okay, so aliens, we can discuss a little bit what maybe alien life would look like in practice. Possibly it would be a very different concept than the one we have now. But okay, imagine this. It's a thought experiment that, yeah, it's not, one can ask, there are still people, it's a world where there are still people. And okay, at some point, maybe the development of civilization takes off, and, maybe one hard threshold is when they're able to go to outer space. Okay, so you just freeze at that moment, and then you compare.
Would you consider us to have met that threshold in our trips to the moon?
We have reached outer space. So maybe you just freeze. But what I mean is that if you had split mankind 3 million years ago, there would be no reason why right now they would be at the same stage as us. They could be like 10,000 years behind in terms of civilization, or 10,000 years, in front, ahead of us. I mean, there's no reason why it should happen exactly at the same time. But okay, you freeze at a certain kind of level of development.
I mean, we saw that, basically, we've seen that happen in with different human civilizations on Earth, wouldn't you say?
Right. I mean, of course, in terms of technology and things like that, progress, is extremely slow at the beginning. And, I mean, ancient Egypt could stay for thousands of years, pretty similar to its original state in terms of technology. I mean, of course, it evolved, but fairly slowly. And, at some point, there was an explosion in the development of technology for humans, which was maybe, I don't know, 200-300 years ago. And, there is no reason why that would have happened simultaneously for a parallel civilization. It's believable it would have happened at some point. So let's freeze, at that moment where, humans are able to go to outer space.
Okay,
just to cross, to go above the atmosphere. Okay, so then you can ask, okay, what kind of math does this civilization have? And arguably it would be still quite different from the one we have. Probably there's no Fermat who has written in his notebook that x to the n plus y to the n equals z to the n has, no solution. Probably, conceivably algorithms have been developed before Riemann surfaces. I mean, conceivably, lots of things are conceivably different, but we can still ask, what kind of math are these kind of aliens interested in? So that's one question. Then you can ask a question about some completely different civilization, completely different creatures, maybe ant-like, maybe bird-like, whatever. Maybe coral-like, but intelligent corals, I don't know. Various things, right? But okay, so what I meant when I told you about what aliens math is like, it was more like about this parallel human civilization, in the sense that my goal was to aim a bit for naturalness, to discuss things that are not contingent to a specific course of events. There's obviously no Grothendieck in that parallel world, right? And there's probably, Poincaré's conjecture is not necessarily a big conjecture for 100 years. There's still quite a lot of differences, but okay, so what I'm asking is, what do these aliens think about, right?
I see. So what criteria are you using? So you mentioned this naturalness. I guess, some mathematics you're thinking really would be common. Whatever.
I would definitely say so. Yeah.
Whatever the evolutionary process.
Conditioned on the fact that they reach the upper atmosphere. Okay, so of course, if you looked at humans 100,000 years ago, I don't think that you could say that they really had math. I mean, probably they knew how to count, but that's about it.
You see their talon marks on bones.
But okay, so I think it goes. I mean, math still goes in parallel with technological advances. And yeah, I mean, actually, so conceivably, these aliens would not have pure math, but conceivably they would. Yeah, I mean,
what would they have if they did not have what do you mean by pure math?
Conceivably, they would only look at applied problems, like I mean, like many civilizations were doing, and yeah, I mean, it's not impossible.
But then, in order to solve those problems, you would say what they have is not. I guess, can you try to delineate what do you mean by pure math exactly? Somehow, I don't see, if you're able to solve a quadratic equation, just because you haven't, said in the same way, here is the class, this is rings of polynomials, and been written the theory. I guess what distinguishes?
I mean, if you want to understand somehow why pure math is not also obvious, just go on the street and go tell a random person on the street about what you're doing in terms of research, and see if they find this natural, or what I mean is that you can say that it's unavoidable that a fraction of the world's population is interested in solving the quintic equation or the sextic equation with Riemann surfaces or whatnot. But you can also imagine a world where this doesn't exist. I mean, in principle. Again, I'm not saying that necessarily parallel civilization is not interested in such things, but it's something that we can consider. It's a question that's worth asking. And yeah, I mean, now there is a big trend in machine learning, as we discussed in the previous video, and there is some fear that maybe computers will solve. I mean, machine learning will solve all the real world problems that we may care about. I mean, it's not completely inconceivable that for building a bridge, that you don't even need to, that in the future say civil engineers don't even know how to solve a second degree equation. It's not inconceivable. And so it's also not inconceivable that civilization maybe would have evolved towards machine learning first somehow, and then kind of neglected some branches of math, and and maybe not have found them useful anymore, and not have pushed the development of those. It's not inconceivable. Again, it's.
I see. Okay, so all right. I want to. There's so many things in what you've said that I think are worth putting aside. One is just that this question about the development of any civilization in terms of technology or mathematics, and whether you say it goes slowly at first and then it takes off at some point. I guess my understanding of history now is actually that there have been. It's not always steady growth. There have been, I think, in Western civilization, in our story, from the time that, I guess we can record, if you want to start, the time of real civilization, so beyond the just individual cities, there have been two major collapses, major times when things took a step backwards, and things, information, knowledge was lost, that all that progress went away and took 1,000 years to get back to the same point, either in terms of knowledge, and sometimes it took longer, or economic development. That's the collapse of the Bronze Age and the collapse of the Roman Empire.
Yeah.
There's
fair enough. And we may see a collapse again.
Yeah, one hopes that we don't. And so there's an interesting question there. How do you avoid that, and under what circumstances does any life avoid those traps? And I think that lots of people have given consideration to the geophysical conditions that allow for life to exist somewhere, but not as much. I don't know. I see these issues as really being economic, whether civilization or technology develops. There's, I guess, there's a couple of different things you're saying about what math might people need or have that seems to hinge on a couple of different things. One might be some kind of natural relationship of the math to the physical world, where you're saying, well, if they had to, if they're on a ground and they have to get above the atmosphere, they have to understand something about the things that we think are in the universe, like gravity and I don't know, pressure, the kinds of the math of basic physics. Do they know the math of, I don't know, some other things that have to go into their economy or anything else to get to that development?
It's tricky indeed. I mean, you're gonna ask the question about North Korea, for instance. I mean, they're able to launch ICBMs, so like technically they're able to go above the atmosphere. I mean, do they have a research in category theory? Probably not really, right? And they're fairly isolated from the rest of the world. I mean, they do. They suddenly read papers from the West and the rest of the world. but you know, there's not like a very deep exchange of information between North Korea and the rest of the world.
Yeah, well, even it doesn't, you don't even need to talk about an isolated separate society like North Korea to, I think, discuss whether a different civilization would have something like category theory, seemingly abstruse or somehow a disconnected kind of thing, maybe a much more philosophical kind of mathematics than the mathematics of gravity, the mathematical model that explains the thing that's right in front of you. And so I guess I just wanted to highlight too, one part of it was whether the math had to do with the physical world. Then there's another thing that you mentioned, which is interest and what occurs to people or some intelligent life to consider. And certainly there's this kind of process of development there. You bring up the idea, what could have happened first, second, third? Maybe a civilization has some mathematics that we can recognize. Could they have found those things out in a different order?
Yeah. Or
at a different time scale? Might one problem have been solved much quicker, or they got this before that? Yeah. That's a tricky point. Was there something else? I mean, you're really starting to see here, well, how contingent is mathematics on something about us?
Yeah.
Something about our own.
I mean, there's, about something about us and something about our history, which is, a little bit different. Yeah, I mean, it's always, fun to think about. I don't know. Technically, Romans could have had cryptography. I mean, some fairly advanced kind of cryptography and slaves that would just make the computations.
Yeah, but they didn't. And what's amazing, we did not really have that's, I mean, cryptography, now that's something I've thought about, now that I know a little bit of its history. I mean, we were still basically using just slightly more complicated versions of the cryptography that the Romans actually did use, substituting their letters and ciphers and whatnot, even in World War II. And it wasn't until the 1970s that people really started using good math for modern cryptography.
Yeah. I mean,
which is sort of incredible.
And it's interesting because, again, to implement those things, of course, it's a bit tricky if you don't have computers.
Okay, computers.
But it's not impossible either, right? I mean, you could imagine like training people to compute, to multiply numbers quite fast and things like that. I mean, it's not like unconceivable. So that kind of math, unlike perhaps neural networks, is not contingent so much on technology. So it's interesting, that it has not happened before. And yeah, conceivably Euler could have had ideas leading to RSA, but didn't. Yeah, I mean, lots of things,
Right, because as what you're saying, that the number theory was so far in advance at that point of the technology, or maybe the different culture, the different group of people who were concerned with communicating and communicating in secret.
Yeah, but okay, so these are fascinating questions, and one can hypothesize quite a lot about what if and things like that. But yeah, okay. Anyway, so I think what I'm often trying to do in terms of evaluating the naturalness of things is ask this question, and of course try to be honest with myself without knowing if I'm being honest with myself, right? And try to not be self-delusional and critical at the same time, still reason about those things.
Sorry, so you mean with regard to your own work, you are
with regard to more like field of research, maybe my own work, then that's it.
But you want things.
I mean, I certainly do ask questions. What there are other questions. I mean, we said, suppose we take an alien civilization. So basically, we branch out 3 million years ago. But now we can, ask other questions. Suppose we branch out a bit later in history. So maybe, what would say Riemann say about this work or something like that. I mean, one can certainly ask oneself those questions. And and if one is not being delusional, often one comes up with the conclusion, and maybe Riemann would have said that's totally nuts, right? To look at this question, and that's fine. I still think it's worth asking these kind of questions. It's not because Riemann would think that it's totally nuts to look at this question, that it's not a question worth looking at. Maybe Riemann was just wrong about some things, and that's fine, right? But I think it's worth asking oneself these kind of questions.
But just to be clear, you're saying you evaluate some approach, and if you think some giant of 19th century mathematics like Riemann would have looked at it and said, what is going on here? This isn't a good question. Or it's somehow not natural. Not natural is bad. You want things to be natural. The aliens will have the same mathematics. That would be good if.
I mean, naturally, that's at least one way of looking at the naturality is only one quality of the math. It's not necessarily the only quality by which one should judge mathematics, but it's certainly a quality that I think one should have in mind.
And can you pinpoint a little bit more what, just say more precisely what naturalness is? As opposed to something, can you?
Well, I mean, again, naturalness is a little bit hard to define, but one way to get a sense of how natural something is without like defining what naturalness means very explicitly is to really ask this question, how would someone who is not exposed to my current environment, look at this? I mean, you can even ask a simpler question, which is actually applicable in practice. How would someone outside of my field look at this? Right. I mean, this already, is something one can do. And there is this kind of there's this kind of general consensus, which I think is quite bad, actually, which is that the experts of a field are the best to judge the quality of the works in a field. I mean, they're not necessarily the most independent people, the experts in the field. And I think at least a great, very positive sign about someone's research is whether there are people from other fields who are looking at this research and are being excited about it. And for instance, I'm being excited about homomorphic encryption, and I think it's a good sign about homomorphic encryption that, someone who has no stake, I have absolutely no stake in homomorphic encryption, actually, likes it and finds it interesting.
Well, that opens up all kinds of issues about, which fields are doing good work. Are they all talking to each other? Are they using the best techniques available? Are they different than another group? Could someone from another field look at something that's going on and say, well, we actually, our techniques just adapted a little bit. We could solve this. Or something if you just looked at it this way.
And of course, some people are not necessarily acting in good faith and all that. So I think the best is to be critical about one's own work, or whatever one thinks of doing. I mean, if I want to start maybe working in a field, then I will start asking myself kind of questions like that to evaluate whether it's it makes sense to devote years of one's life to work in that. I think there's a lot of good ways of judging how interesting something is, and
well, interesting is another one.
Interesting maybe is a strong word. Yeah, natural is part of interesting. Interesting is more than just naturalness, I think.
Well, can I just say what I thought you might have said about saying whether something is natural. Maybe a different mathematician might say that when something can be viewed as part of a larger framework, then they begin to see it as there are all these people, certainly in 20th century mathematics, who tried to give a structure and generalization to the whole thing, who viewed everything within one language of schemes and topology and algebraic geometry, and said, well, now we can apply this to everything. And they would, maybe a technique that someone used in a proof, they don't like it if it's like a trick to them. Someone just cleverly did something. But if they can see it, like if they've already defined an object and it's supposed to have these properties. Oh, what you were supposed to do is use some kind of cohomology theory. Then they view it as natural. I don't know if that's has to do with, because as far as I can see, those are all very different ways of approaching the same.
I think these are two different ways of approaching, what naturalness means. And I don't necessarily agree with the vision that you said you expected me to actually promote.
Well, not that you would promote it.
I mean, I think that it may make sense to ask a question like that. How does it fit in the grand scheme of things, etc.? But one should be extremely careful about the way one develops the grand scheme of things. And I think one introduces a lot of biases, in the way one develops the grand scheme of things. I don't have maybe enough wisdom to say that the grand scheme of things could have been made different, etc. But there are many fields where, for instance, probability. Okay, maybe I don't know to what extent you want to go in that direction, but probability is supposedly founded after Kolmogorov axioms, and it's built from there. I mean, that's the way its probability is
in the modern world. But I guess this.
But what I meant is probability could have been constructed completely differently, and what is natural then becomes a completely different question in that different construction. That's what I mean.
Well, I guess I wonder now when I think a lot about the history of mathematics and how it could have been different. Because look, people a long time ago had to have insurance, probably, right? There were voyages that people had to fund, and so someone had to think about what were the odds that the ship is going to wreck and they're not going to get it, or whatever, right? Someone had to think about those problems. I don't know what was the ancient understanding of probability. We know in the more modern world, like by the middle, people were playing card games and gambling, and that is what ultimately began, I think, the modern combinatorics and probability. But
okay, what I mean is, okay, if going back to your definition, to what you said about naturalness, I mean, if you start building probability from Kolmogorov's axioms, then some questions appear to be very natural, yet you could construct probability fairly differently, and then some other questions appear to be fairly natural. So one can ask questions about the naturalness of the framework that defines natural questions, and that I think is a little bit subtle. I mean, similarly for set theory, you could construct much math from type theory instead of set theory. Type theory being much closer to computer programming. I mean, the way that people think of computer programs is, like an integer in a computer program is a type. It's something that allows you to do things, but you don't really think of the set of integers so much when you work with computer programs. You think more of the type. What can you do with this concrete instance of an object? Okay, so you can construct a lot of things from there, and then a lot of things that seem natural in the previous way, in the classical set theoretic way, appear maybe not as natural in the type theoretic approach. And you know what I mean? Okay, it's that naturalness is a little. I mean, naturalness as being the simplest questions in a construction of a framework, what appears to be at the bottom of the construction. I think it's very contingent of the very way you construct the framework. So maybe natural things are not as natural as they are claimed to be. I don't know.
Right, and I think that's a good point. And I think that my own hypothesis would be a lot of what we consider to be our frameworks are somehow the most contingent. Maybe the particular results interpreted against physical, things, against experience. Somehow, a different society will have to have some kind of analog. It could look very different.
Yeah.
But they have to overcome the same kind of problems somehow.
I have just a small anecdote. It's I used to work more, but I still work with a good friend of mine on the easing model business, and I mean I like very much high-level things about the proof, and he likes to be quite more careful about the details. And you know, sometimes I would just write things, and he said, you know, but okay, how does it, you know, like if I try to apply the definition, it just doesn't make sense what you wrote. And I would often say that if the statement actually is contingent on the definition, it's probably not a good statement. Okay, that's a little bit extreme, but it's more like a joke. But there is something that I meant, you know, genuinely here, which is that you're trying to describe, you know, a random curves that arises in a model, etc. And if your construction is actually the fact that your construction can be made is contingent on, you know, I don't know, Kolmogorov's axioms, say, on some sigma algebra, on some kind of subtle technical point that's a bit tricky to define properly, then maybe you know, you know, we're not going, you know, bringing the insights we meant to bring. So yeah, okay, that's what that's you know what I meant.
Well, that also yeah. So probably I'm going to guess that same alien civilization with different math, even having achieved all sorts of feats, probably would not have the same definitions of objects, the same framing that we have. A lot of our definitions, you know, sometimes they're convoluted in order to handle particular cases, especially trivial cases. And you know, maybe you don't need to handle those cases. You really care about something. You did not need to, you know, the way we choose, I guess, to put forward.
Yeah, maybe aliens have a big O notation for putting all the special cases, you know. You know, we have a big O notation to abstract constants and things like that when taking limits. But we can, in principle, imagine that there's a big O notation for whatever I didn't mean, you know, or something like that, right?
Yeah. So okay. So I think we said talked about some things that are contingent. Do you have any? Is there anything that guides your sense? Do you have an example of like what's the closest to be like an alien life? What there would be a different mathematics? Did you see this movie?
What is similar is easier to. What is likely to be similar is easier to envision, of course. What is, you know, not in our math, for the very reason that our math is not developed in those areas where the alien civilization is very proficient in, right? But okay, maybe let's still start with the easier question, which is what math do aliens have? And so I think, you know, again, going back to the discussion in the previous video, I think it's hard to imagine they don't have numbers. I mean, integers, like it's hard to imagine they don't have integers. It's hard to imagine as a result they don't know what is a prime number. It's hard to imagine they don't know fractions.
Well, okay, I guess I don't know about this kind of speculation. Yeah, because we're thinking about our own development and how we needed each thing.
Yeah, but okay, numbers, you know, appeared independently for many civilizations, for instance, right? I mean, so that's a good hint that numbers, you know, things that aliens, at least in the sense that I defined them previously, would know about numbers. Then, yeah, okay, so, you know, things that seem very natural to me about more advanced math, more advanced than numbers, and maybe, you know, basic number theory would be maybe group theory somehow. That seems already less straightforward as a notion. I mean, less natural as a notion, but still very natural. Like group theory is definitely something that I think aliens would know, or very advanced aliens would definitely know something about finite groups, perhaps, I would say.
Well, I don't know, you know, finite groups came about when people were trying to solve polynomial equations, right? That's how people thought of them. Right. And I don't know, I guess I can imagine a world where people thought first of continuous symmetries of space.
Sure.
And somehow, I don't know that you really...
I mean, finite groups of transformations, you know, I think groups are still best thought of, you know, if terms of collections of transformations, I mean groups of bijective transformations of permutations. I think that yeah, it's true that they came to be when we were trying to solve quadratic equations. But to me, it sounds actually strange that we defined permutation groups after we, cared about solving higher degree equations. I mean, yeah, that doesn't seem, it seems it could at least very well have been the other way around, that people somehow cared only about combinatorics fairly late in history, even though it's one of the more elementary things. So
yeah, I guess I could have, yeah, maybe people could have been interested in more card games like Cardano was playing.
absolutely.
And came up with some of those things, but actually, frankly, a lot of times I'm just in math history, the same idea actually needs to appear multiple times before anyone bothers to formalize it, because otherwise they're just thinking of it in that context, or they don't think it's important enough. Well, people did a lot of linear algebra before anyone decided that there should be a subject linear algebra.
Right. So I mean, about more advanced math that aliens have that we don't have. Well, that's
really speculative.
That's very speculative, of course.
But wait. I wanted to what I was actually trying to get to. I have a few examples in mind in my head of what I think are like the closest things we have to what it would be like to communicate with a different intelligence. And I don't know, you can see if you judge these examples to be any worthwhile at all. I love this the thing that I have on on my channel page is this Plimpton 322 tablet, which I've now mentioned a couple of these episodes. And this is a relic, an incredible relic of, so this is human mathematics, but it's from a society that we have very little connection to, right? Because this is coming from the time of Hammurabi, probably. We're talking about nearly 4,000 years ago. Civilization, we don't, there's not any real continuity between their language and ours or the mathematical development. And we took this tablet with a lot of markings on it and essentially tried to decipher it and interpret it. And we see what sort of, some kind of mathematics they were doing. And we can read into it, a whole lot of concerns. There's some debate over what exactly is the right way to interpret this. Have we talked about this before? Do you know what I'm talking about? No?
It's fascinating. No, we haven't.
So okay, I've mentioned this. I know I've mentioned this in a couple of my other discussions, but this is the most incredible object. It was at Columbia while you were there, and it's not a big deal. They have it at the Columbia Library. If you go to the rare books section, in fact, now it's not even on display. People don't know, but I think this is such an incredible artifact that changes your whole view of history, because it's really the oldest thing that I know with some non-trivial mathematics.
Oh, wow.
And not only that, but it's actually a lot more non-trivial. It's quite far in advance of some later Egyptian mathematics that we have. We have papyri from quite a bit later, which is, school exercises to train people to solve linear equations and, making fractions and, putting everything in lowest form. But this tablet, here's columns and rows of numbers. They're all written in base 60 in cuneiform, right? So we figured out how to read these, and we also figured out how to read Akkadian at the top. And what these numbers are, what they appear to us is being the length of a side and a diagonal of a right triangle. And they're very big. They're not 3, 4, 5. It's not 3 and 5. There's some big ones here. Real big.
You mean integer lengths?
Integers.
So Pythagorean triplets.
Pythagorean triples, exactly. And then they have one over. They have the cosine in another column. Okay, it represented in their base 60, format. And some people have suggested, look at what this means. Look at what they must have been obsessed with, right? They had to do trigonometry. They knew, so 1,200 years at least before Pythagoras, they had the Pythagorean theorem. One can read into their obsession, their interest, as though they somehow appreciated the same thing about the Pythagoreans figured out about irrationality. You know, maybe they didn't like it, and their goal was to find integer Pythagorean triples or rational cosines in order to do trigonometric calculations. And they found, they must have found some way, which involves quite a lot of number theory probably, or arithmetic geometry, to produce that set of triples.
Yeah.
Right, and it's just this. And so some people have interpreted this as a cosine table. I mean, it's listing a whole lot of rational cosines, you know, in a prescribed range of angles. You know, as you increase or maybe as you decrease the angle. Right. So there you see a very different set of concerns, maybe, to someone like Ptolemy was actually trying to, you know, calculate cosine of 1 degree and approximate it. Cosine of 2 degrees. Well, lots of people will have to, and of course they had to use this because, you know, we understand they had to understand astronomy. They had to understand the motion of the sun and what is a year once they had big enough civilizations to care about agriculture and regular, you know, mass scale agriculture.
Yeah.
Right. Some people have put forward, oh, maybe they didn't know Pythagorean theorem and maybe they weren't so concerned about rationality or irrational numbers, and it's just an exercise in the quadratic formula, which we know that they had from other tablets.
Yep.
And they just solved quadratic equations according to, you know, this one, next one, and produced essentially the same table. I don't know. I feel like that this artifact is like you know, it's starting to get in the direction of looking at a different mathematics.
Absolutely, absolutely. It's actually more spiritually motivated mathematics to some extent. It could be. I mean, I know a lot of math was developed initially by astrologers, or, you know, I don't think there was a, you know, back in those days you were a mathematician / astrologer / priest / many things, but. Yeah, some mathematics was developed for accounting, and some mathematics was developed for astrology. Some mathematics was developed for engineering, and some mathematics for, you know, just, you know, explaining things about the world. And yeah, I mean, depending on your, you know, what's your drive, yeah, then you definitely push in some directions. I mean, you can go maybe to Diophantine equations, or you can go to yeah.
So I think it's maybe a surprise to some people, especially, you know, I don't know, given today, if you look at a cosine table at the back of a book will be very different. If we're not concerned with finding rational cosines.
Absolutely, absolutely.
With 8 decimals of, you know, just a standard ruled, you know, 1 degree at a time or something like that.
Yeah. No, absolutely. I mean, one could imagine, I mean, you know, more contemporary, I mean, you know, if instead of having 1 person in a billion like Ramanujan, one had 1 person in 1 million like Ramanujan, right? How would this, you know, affect mathematics? Probably would be very different, right?
Well, yeah. What if people were different and, you know, if, I don't know, some kind of genius? Again, I'm inclined. That's an interesting question. Again, I have just put out my hypothesis, not to go too deep into this tangent, but it's my assertion that I think the real, the limiting factor is not that genius only appears in so many people, but it's the economic structures that allow or disallow people to develop or utilize their talents.
No, of course. I mean, that's the bigger factor, obviously. But still, I mean.
Okay, so I have a couple of other examples. So, so that is not really alien life. That's just a different civilization.
Yeah, different.
And we could look to the Mayans or something as being a little bit similar, but I don't think they were quite as advanced. What about when we learn other languages? So that's why I think you didn't hear me before. I asked, did you see this movie Arrival from a couple of years ago?
Actually, no. I read the short story, but I didn't see the movie.
Oh, I didn't realize it was Basically, so this is the short story. Also had
Very beautiful.
aliens come to Earth, and then this
Yeah,
linguistic.
the movie is based on a short story, which is very, very beautiful. It's not so short, actually. That short story is
Okay.
like 50 pages or something, but it's a very beautiful and moving short story, actually. I highly recommend it, but I haven't seen the movie yet. Yeah.
But you
Yes,
see that,
okay.
but presumably this is the story about you know, you encounter these, and the whole problem is how do you communicate,
Right.
and you have to figure out their language, and you know, today we actually have the kinds of techniques. It's really a machine learning kind of problem, right? To some kind of classification. If you can go back and forth and receive any kind of feedback, or see what happens when you put one thing out and whatever, to read and classify what the different alien language is.
Yeah.
And so the way that works is a kind of, you know, is that the same? It's not quite the same thing as mathematics, but it is a different, it's some kind of different structure that we didn't come up with.
Sure.
And I think, so we
language.
haven't actually encountered aliens, but we have tried to do what they do in Arrival with other species that have languages on Earth. Right? So I don't know how much, are you aware of how we've tried to learn other creatures' languages?
I mean, some of these things I've heard, but I'm not very aware. But so go ahead, tell me what you know.
Well, I after seeing Arrival, I tried to look this up. Like, have we done this with whales? Like, because you know, whales communicate you know, orally, right? But whales, as much as we know that they must have some kind of complicated language, it's just too hard to learn their language because we don't observe them enough.
Yeah.
Right, in the natural world, like, you know, it's just too hard.
Yeah.
But
birds are easier, probably.
Huh?
Birds are easier to study, probably.
Maybe, but I guess there are a lot of animals that make noises, and yet their languages turn out to be not very sophisticated, like dogs and cats. They do make some, but they.
Yeah, of course.
But it turns
I think
out
birds communicate. I mean, some birds. I mean, there's a lot of birds, of course, but some birds actually communicate very interesting information. So,
really,
I mean, there have been studies about, you know, information propagating. I mean, for instance, learning. I mean, know-hows. I mean, learning how to open some kind of boxes and things like that. It's been studied that, you know, some bird has at some point figured it out and then explained to others, and some people have studied the propagation wave of that knowledge.
Really?
In the UK, yeah, because at some point they learned how to open some milk boxes or something like that, and yeah, I mean, they definitely communicated with one another. To what extent it was, you know, purely oral versus show how to do it, I don't know, but there was definitely, you know, a communication, and it's very interesting, actually. It was in the 50s or 60s, I forgot. I'll try to find it.
No, where, you know, birds, they just sort of communicate like, here's my position and I'm ready to mate.
Apparently, in some situations, I mean, for some species, it's much more than that, even though, of course, yeah.
Well, okay, so as far as I'm aware, in the reading that I did, I believe that the species with the largest language that we've deciphered the most is prairie dogs.
Okay.
Prairie dogs, and what's special about them is, one, they're easy to observe because they will be just in some field. And they're a creature that they live in these holes in the ground, and they have a lot of predators. And so they have sentries that stand and just watch, and they yip and whatever. And their yips are actually enough, sophisticated enough to communicate a lot of things. We've found out about what direction things are coming from, how large, what color.
Okay. Wow.
Right, because you know, researchers were able to come and hear their yips when they presented with a yellow sign versus a blue sign, and it's consistent, and whether it's someone's big or something small. And we just analyzed you know, we just took a you know, the signal that we heard, and you know, classified it as saying all these different things. So, I mean, that's some kind of working that uses something.
Yeah, I know some animals also have names for one
They have
another.
names. Amongst
Yeah, I mean,
themselves.
perhaps dolphins or something. I'm
Probably,
not
yeah.
sure.
I guess maybe they've seen
Uh,
that.
yeah,
I
well, it
guess
makes sense that identities would be, encoded in the in what they say. But yeah.
so. I guess I don't know if this quite gets as far as a different civilization's mathematics, because all we're still crude in the way that we have to try to decipher their system, because we're limited in terms of what we can recognize and think. Are they thinking of big and small in quite the same way we are? Well, we don't know, but that was the best with the data we, as that's as precise as we could get.
Mhm, mhm.
Um,
No, I mean, of course, the kind of math you do depends on your senses. I mean, and that's why I prefer to focus on other kinds of humans, because then if you imagine creatures that don't quite see in the same way as we do, actually maybe who maybe just the way maybe if they see like bees see, which is quite different from the way we perceive light, then it just becomes a completely different world. And I think the resulting mathematics is probably very, very different in many ways. I mean, geometry just becomes a completely different thing. And yeah, I mean, I'm happy to hypothesize as much as you want on your channel for you, and for the entertainment of your viewers. But I'm just, as a caveat, it just becomes very, very difficult to.
the only other thing I guess I had in mind when
Uh-huh.
you mentioned this is this research I was really fascinated by about learning some things about how the brain works. But here's another system that does its own method of calculating that could be very different from what we've actually consciously figured out. I don't know if I've ever mentioned to you these things called grid cells in a rat brain.
No.
Oh, this is a wonderful thing that people have now been able to figure out some. I used to, I'll say, I was always skeptical of neuroscience if they just said, oh, this part of the brain lights up, so it must have to do with when they were thinking about this and whatever. And that tells me next to nothing. But now people are actually able to read off from those electrical signals, much the same way as learning a language, exactly what they're actually communicating, what they're registering.
Mm-hmm.
And this has led to some, in the very simplest of cases, this has led to people being able to read what the brain is saying. I mean, maybe, did you see that presentation by Elon Musk?
Neuralink, you mean?
Neuralink?
No, not entirely, but yeah, some parts. Yeah.
Well, I think maybe one of the more impressive things demonstrated, I mean, they demonstrated they could do a surgery and it doesn't hurt the pig or whatever, but they demonstrated something that has actually been done even better, I think, by a group I know at MIT, where they showed, like, here is electrical signals coming directly from the brain. And we've trained a network to read those electrical signals in terms of predicting the position of the pig's leg. And here's another device that actually is registered in real time, the actual position of the pig's leg. And so you can see that they've learned to read the language of the brain because it's exactly, they're able to predict what the leg is doing just from electrical signals in the brain. Right, but my guess is that they used a lot of supervised classification. I don't think anyone really believes that thing is just for that. They're sort of extracting that information from that signal. But there was this great research done at MIT where they in an unsupervised way looked at cells in a rat's brain, which were suspected to have something to do with its head and the position of its head relative to a room or something. and figured out, they took these signals from many neurons. And so it's a point in some high dimensional space. And then they projected down to the most important components. And it creates some kind of manifold, or like a kind of fuzziness. Points clustered around some. It's like a circle, but with waves embedded in 3 space.
Mm-hmm.
And it turned out, so from any signal, you can project it to some point on that curve.
Mm-hmm.
It parameterized that curve by arc length, and this somehow actually is the head angle. That once you adjust for the phase, you can just take any signal and predict what the rat thinks its head is at, and then they actually put a camera on its head, and it lines it up. So we read the very way that this thing is calculated, and it's like its own kind of computer system where it has thousands and thousands of neurons just for this one-dimensional quantity, because each one has a lot of error associated with it. It has some Gaussian curve of when it activates, when the head is in some range, and it does its own error correction and everything in order for the rat to have some sense of where its head is at, even if it's hard to know whether the rat is conscious of it, but its brain is calculating it. And when you go to a 2-dimensional problem, rats are also able to localize their position somehow. And they found these these cells they call grid cells, because they, I guess I have to imagine like a camera from above looking at a room,
Mm-hmm.
and you just place a dot whenever a particular neuron fires,
Mm-hmm.
like a dot for where the rat is,
Okay.
where the rat's head is when that neuron fires. And you do this, there are certain cells, and you'll see they make a lattice, a 2-dimensional lattice in this place, and different cells will correspond to, a cell in the same cluster will be different residues modulo that same lattice. And then there are different lattices, cells that register along different lattices. And somehow those cells all send their signals to what they call this position cells, that somehow know their position in the whole room and don't have the ambiguity of all those points on the same lattice. Does that make sense what I'm saying? So it's like it's using the residues
Mm-hmm.
modulo different lattices that are being recorded somehow by those other by the different grid cells.
Okay.
And they're doing some kind of calculation, which you could view as the kind of Diophantine approximation in some sense, or it could be like the Chinese remainder theorem, but in 2 dimensions, if you discretize.
Uh-huh.
To figure out, to localize its position more accurately, even though the area is large, and probably because it's in an environment that's evolved where cells can only keep track only a little bit, accurately only a little bit in 2 dimensions at a time, and they fire along all the positions of a grid. But if you have multiple grids, you can be accurate in a larger space.
That's very, very interesting. I didn't know about this.
Oh, this is fantastic stuff. This is people are actually figuring out how the thing really works. How this thing actually learned to calculate. You can imagine that if people had calculated using residue number systems instead of our decimal system or something. I don't know, but the brain does it apparently.
Oh, that's really amazing. Yeah. I mean, and it raises a lot of questions about how life could have been different and things like that. I mean, okay, so somehow what I intended to discuss initially, I mean, I'm very happy to discuss this, but you go extremely quickly into a territory I have no idea. I mean, I know too little about. But okay, so there's a question: what is math? I mean, going back to the question of what is math? What is math? I mean, and I mean, we have a modern definition of what is math, and even without kind of definition or kind of common sense understanding, sometimes it's not quite clear what is math, what is another discipline. I mean, is accounting math, for instance, or as, I mean, if you typically, if you go to, I don't know, the barber or something like that, and you say you do math, then they think you're good with numbers, and then they think you're an accountant, right? And so
I have had that
but
experience.
usually you don't consider accounting as math.
Yeah. I had that experience with a career counselor, and I said I do.
Okay.
They're like, why don't you be an accountant? And,
yeah, right. I mean, you're good with numbers, right? And then then you say you're good with complex numbers, and then they're confused, right? But no, so there's this question of what is math, and so I mean, currently we define math as being, about statements that we derive using rules that are underlined by some logic. And this logic actually, at the beginning of the 20th century, we kind of defined it even more precisely, but it was always implicit in the works since, say, Euclid. Then Babylonians, what's interesting about them is that I'm not sure they were proving theorems, or maybe they were, but they were definitely doing things that mathematicians are doing, and at least that are interesting to mathematicians, for sure. And they were interested in the same kind of questions, but maybe they were not so much about theorem proving. And same for Chinese mathematics, which I'm not sure was so much about theorem proving as much as it was about, studying questions in some ways, but not necessarily proving theorems. A bit like also theoretical physicists, for instance. Now they may be interested in questions that are also interesting to mathematicians, yet they don't do it. They don't really care about proving things or things like that. So so there's this question of what is math, but if one puts it, one says broadly speaking, a bit beyond the question of proving theorems, it's about caring about abstract objects, as opposed to objects that we have concrete instances of in our lives. So, and as a result, if you do something like that, then you start putting economy into math, probably a part of economy into math, part of computer science into math, a part of physics into math, and that's fine. I think. But okay, that's what for me, I guess math would be. It's what we call math nowadays, plus a little bit more, this kind of abstract things that we think are, people think are important. Okay. So
can I just in case you have any kind of insight into this very old philosophical problem? Well, we've spent a lot of time talking, actually just talking about the historical contingency of math, and not so much about the things. I imagine some people out there really think there's something that math has to do with the, with the universe. It's somehow inherent and natural. Do you have anything to offer in that direction of your sense of how math inherently relates to the real world?
Well, I mean, okay, so there are a couple of obvious things. I see nothing in the universe that says that, the universe is about theorem proving. So, I mean, that's a negative thing about this statement. Positive thing about this statement is that obviously we would not have started math if, if we didn't have some concrete physical problems to study initially. There's no way we would have invented calculus if there was not some physical application.
But okay, keep going.
I mean, okay, there's no way that at this stage of our civilization we would have invented calculus if it didn't have any practical application. Then there's another obvious statement, which is that math runs in our brains, and our brains are made of atoms. And so as a result, you can say that still, to some extent, math is still about this universe. Okay, so I said these three things that I think are fairly obvious, but okay.
I guess, I mean, maybe you're right to talk about theorem proving as one of the things that we take to characterize the way that human beings do mathematics. And you say, yeah, in ancient times, it seems like they weren't so concerned the way we do today about the theorem proving. And yet somehow I guess I'm inclined to think this is not quite so important, because if they weren't able to get a good result, it wouldn't, you know, it wouldn't perpetuate. And so anything that people did solve, it did involve the same kinds of processes as proving.
Rigor is important. Yeah, I mean, in order to be able to, scale things up, to put blocks on top of each other, to create a tower of knowledge that is stable, you need to make sure that your blocks are stable. And indeed, at some point, if you want to scale things up in some sense, you should have a rigorous way of reasoning. Does it need to be as rigorous as the way that mathematicians think of theorems? I mean, I would say not necessarily, in the sense that, for instance, chemistry has evolved quite independently of math, I would say. Like, chemists, they can be very talented with, estimates and things like that, but there's not so much theorem proving, at least at the level of at the rigor level of mathematics that is happening in chemistry. So you could say indirectly, through physics and through the fact that physics is much more connected to math, then some things permeated to chemistry. But I think chemists, they know how to do their job fine, without really needing to prove theorems. I may be wrong about this, but I think there are lots of things that we know how to do in the world that do not rely very much on theorem proving, or like building a car. To what extent does it rely on theorems that are proven, as opposed to known to be true for intuitive reasons? Of course, one needs to kind of feel why things are true in order to progress and things like that. But yeah, one can still ask the question to what extent rigorous math is fundamental to the development of technology or sciences. And yeah, I mean, I think it's a fair question to ask. But of course, some level of rigor is, and some level of discipline in terms of manipulating abstract objects is necessary. And I think, yeah, it's clear that Babylonians, they were very sharp, very precise in their way of thinking, and we are not necessarily better. I mean, we have much more formal things, but yeah, I think they were very correct in what they were saying. It's important to be correct. I mean, but again, proving things, that's a little bit different, perhaps. So
it's true that yeah, there's a different view in these different disciplines. They don't attach the same weight, the mathematicians do to the proof, and it's not clear what even proofs exactly are when you talk about physics or experimental science.
Sure. I mean, there's a general sense of what rational thinking is, which is very necessary for anything related to the science or engineering. But yeah, it's otherwise.
I would point out, you say, well, if we didn't live in the physical world presents us with the kinds of situations that call out for describing things with functions, and therefore calculus.
Yeah.
Right. But you can imagine people developing mathematics of games of chess or cards or something, and there's a whole lot of mathematics that we would call mathematics there you could have developed, and somehow never looked at the world of falling cannonballs or anything like that.
Yeah, I mean, actually, that's something interesting. I had not thought about this, and I think I can explain why I had never thought about this. Because at the time I thought about why calculus came to be. For instance, there was no program that used neural networks to play Go that existed, or chess that existed, and so calculus was irrelevant to playing Go and chess, for instance. And so I didn't think so much about that at that time. I was, when I was younger, I had this existential doubts about how things came to be, and why do we study this? Why do we have 6 hours of calculus of analysis? We call it analysis in college here. Why do we have 6 hours of analysis a week, and 3 hours of geometry a week? There are questions like that. I was wondering, and yeah. Okay. Anyway, so you're right that in principle, if your only goal in life is just to be the best chess player ever, you may end up discovering calculus as a result. It's interesting, yeah.
Oh, okay. So I wasn't even.
I still think that the way we understand calculus, etc., really came from the physical world. But one could make a case that it's less contingent on the physical world as it first appears to be. That is a case that could be made. Or just that if you are only people who don't care about the physical world but just care about money. Imagine you just have money. If you start using money, you end up very rapidly with the notion of real numbers. I mean, even at some point,
I feel like real numbers. Just with
and then optimization as a result, optimization.
I see. I certainly think anytime if you have to measure lengths of things, you're going to be led to.
Sure, but that's the physical world, huh? Lengths.
And that's the physical world. So
that's already the physical world. And but I think that if you are just a civilization of merchants and you don't care about the physical world, you're happy with your level of technology, you may end up still, it's true, you may still end up discovering things about analysis. I mean, derivatives and things like that.
There's a lot I think we could go on about the historical contingency and different ways that things could have been gotten to, or different ways from the way that we have that probably could address some of the same problems. Like you can imagine a civilization that actually doesn't have analysis or calculus and does everything discretely, and everything is done with computations and polynomial time or something, and yet they manage to get in approximations to a lot of the same kinds of results.
Right.
And that somehow captures all that they need in order to send the rocket ship into outer space.
Correct. That's entirely possible. And what I think this is now becoming a little bit more obvious because of computers, in the sense that I think it's entirely possible that future generations will not really know about calculus, and they will just know about something that, I mean, they will start with knowing computers. Actually, that's even the way I learned what P versus NP was before learning what epsilon and delta were, right? And I think it's not even so far-fetched that in the future, in maybe 50 years from now, people only learn about epsilon and delta in their PhD. I mean, it's not that crazy. I mean, of course, things change and things like that, and so it's not even that crazy that you would learn about epsilon delta only in grad school. So yeah,
that's why I guess what I was trying to ask about is whether you thought that there was something really, some irreducible, some inherent relationship between math and something experiential, either physics or something else in the real world. How you reconcile the same problem that Plato had between these the idealized abstractions and the things that you encounter in life, and whether you had any answer to that conundrum. Not that you have to.
Yeah, I mean, I would say it's extremely hard to do to be good at calculus if you don't have an experience of the physical world. And well, generally speaking, what the real world is for you when you're just a small creature on a planet is largely also determined by the other creatures around you, and particularly the other creatures of the same species as you. And so, okay, that's your reality. Then what I think is that it's extremely hard to honestly do good work in mathematics. I mean, for me, it would be impossible if I didn't have some intuition that came from the real world experience. By real world experience, I really mean just the fact that I know about basic geometry because it's just the world I live in, and I know that if I draw a shape, put another shape in it, how things will look like. This kind of geometric reasoning, it's so fundamental for doing anything in my research, even though I'm not a geometer, right? So yeah, I think that basically if you don't have this kind of real world experience, then you become you're as bad at solving a problem, at proving things, because it's my job, I guess, to prove things, as computers are currently, and they're not very good at that. And and for them it's still much easier than for us, because we have already developed the math. They just, what we want them maybe to do now is to be able to learn to do the things that we were able to do, which is much easier than inventing those things to start with. So yeah, I think it's very hard to say something useful in the current mathematics as they exist now, if you don't have some kind of physical experience of the world. Then yeah, maybe there's some things that are extremely abstract, and I don't know how people who are in these very abstract fields work. I mean, are they better than computers at their own fields, for instance? Are they better than brute force simplification of equations? I mean, honestly, often those people live in, I don't want to, maybe that's the time when I start being a bit controversial, but many people working in these very abstract fields of math, they are not so easy to discuss with anyway about these questions, and they would often dismiss this question as irrelevant or stupid and things like that. So which makes it not so easy to determine in the end the answer to such questions.
What question are you asking them?
I mean, to what extent is your field just a trivial thing that could be done by a computer, right? I mean, first, you cannot come and ask this question directly, because then you get problems with people, right?
Yeah.
But it's still a question that I'm asking myself quite often when I see some things in some fairly abstract areas of math, which are obviously disconnected to the real world in any, in any way that is made explicit by the researchers, at least. Okay, so yeah, and I will not give more specific examples because I don't want to make enemies on your channel. But yeah, I think there's a lot of fields where you can ask, you could ask this question, if you're not using your physical experience of the world, what are you using concretely to solve your problems? Because if you're playing chess, if you're playing Go, I know you're using your intuition of the world. I'm not a great chess player, but I mean, even at the level where I am, I mean, of course, I'm using my intuition of the world implicitly to play this game. I'm not playing it blindly because, yeah, I use the wiring I got initially, that I got initially by learning to walk and evolve in this world to play chess. And it's not specific to me. It's just anyone who plays chess is using some primitives that they already learned in the geometry of the world. And that's how we invented chess as well. But yeah, I mean, it's interesting to think about this question that you asked.
I do. I guess I do appreciate what you said about the role that calculus plays, even in an abstract or a discrete thing like chess, probably in the way that you evaluate the relative strength of different positions.
Exactly. So if you really care about this, in the end, maybe the only solution is to do something like these neural networks that play chess. Maybe this is the best way to play chess in a given computational envelope. I can imagine. I don't know. We don't know, of course. No one knows. But I could imagine this: if you have a GPU, doing a neural network to play chess is the best way you can play chess.
I guess what I was trying to ask was whether you had were a Platonist or abstract entities and their relationship.
Yeah, I mean, there are several answers one can give. I mean, one can give the purely Platonic answer. One can give the I'm discovering things, and I'm a creator, and my theorem is not more engraved in the stars than Harry Potter is, or I mean, my paper is my piece of work. I'm a writer. I write a piece of work, and yeah, Okay, so and then there's also the possible answer is that it's not an interesting question. That's also a possible answer. And another answer would be that it's something in between all these things.
Well,
but yeah, okay. So where do I stand myself? I'm happy to answer if that's your question.
Well, do you have maybe to refocus? I'll now pose that question, but also I think in a modern guise, the same question was asked in this famous essay of Wigner, or Wigner, I don't know, pronounce it, this unreasonable effectiveness of mathematics and physics. I think he's, the same issue is coming up. Why is it that this mathematics seems to play a role in the real world, whereas to him, a physicist, it was very abstract, seemingly, and not necessary. And he specifically gave this example of the complex numbers as something he thought mathematicians just came up with as just playing their own games or to satisfy their own aesthetic concerns. And yet in his physics, it's there. And just to try to tie this whole thing together, right? I thought at the outset that this conversation about, what math aliens would know would somehow concern with this very issue of what is the necessary, what is the math of the world versus the unnecessary or contingent math of, well, this is just the way we do things. This is just our concern. This is just the way we phrased it or whatever. And so clearly Wigner had this conundrum, and I think it's basically the same kind of, in a different guise, the same conundrum that Plato had about the relationship between the abstractions that he could understand precisely, but the real world objects that are part of his experience, but that he could use them as models, but they never.
So I think it's fascinating, your question, but it's fairly complex, and I would, it's not obvious to me that these are the same questions. I'm not saying they are not, but it's not obvious to me that they are the same question. But okay, first things first. So if you want my answer about, where do I stand in terms of Platonism versus other, views? So I think that obviously, if I ask a question in math and I manage to get an answer, that answer could not have come up different. If I ask a concrete, maybe yes or no question, that answer could not have come up different. And as a result, it's a strong case for Platonism, right? Like you discover an answer. I mean, maybe actually, sometimes I'll ask myself the question, I phrase it this way. So I ask a question to math and math answers to me, right? I mean, I multiply two numbers and I get a number. And of course, that number is not my creation. If someone else did it, or it's not contingent on when I would do this calculation or something. I get what I get. So if you ask a question, you get an answer. So that's one thing in favor of Platonism. Then there's the other question is, what questions do you ask? And that's completely different, right? What do you choose to push? How do you choose to organize your kind of tree of knowledge, right? And it's clear that if there was even another copy of me that had just tiny different experiences in their lives, they would not exactly develop exactly the same tree of knowledge, right? So yeah, I mean,
so you've
that much is obvious.
Yeah.
Then, you could say that Harry Potter is also appearing in the digits of pi. So maybe Harry Potter also is, a creation of God or something, right?
Wait. I don't know if I understand. What are you? How does Harry Potter appear?
Well, I mean, because all the digits of pi are kind of. I mean, they contain basically. Probably we don't know how to prove it, but they contain all the possible finite length strings somewhere, right? Well, of course, maybe all the information then is just translated in the position where that pattern appears, and maybe that's just just not saying much. But you can still ask. You can still say that it's about focusing at the right place in the digits of pi, right? And so similarly, I can say also, my math is about focusing, about asking the questions at the right places, and about growing something. And it's about making a lot of choices or a lot of inputs that are mine. So I think it's it's a bit between both Platonician and Aristotelian views. It's you still choose what you do in the end. I mean, hopefully, and the answers you get are kind of universal. They follow some rules, and they're kind of universal. And maybe they were awaiting you, like Harry Potter, was awaiting you if you went far enough into the digits of pi's, right? Yeah, and maybe it's a bit more on the natural thing and Platonician view than the Harry Potter thing. Maybe it's more, but it's maybe just a spectrum. That's what I mean. And so, yeah, that's basically what I have to say about this.
Well, okay, I feel like you've tied in this other question, this other philosophical question people ask about whether mathematics is invented or discovered, and you've.
Well, I thought that was the question. Sorry.
Well, I mean, I guess what you see, I guess it naturally ties in as you seem to have assumed. I mean that discovery, if mathematics is discovered, then there's something about it was already there to be, that somehow these idealized abstractions or theorems or whatever, what have you, existed in some sense. And the invention part of it, you're attaching to this historical contingency and experience of the world. I guess, maybe something I'd push on that a little bit is, well, people can ask all kinds of questions, but there seems to have been something, only some of those questions are good or only lead in some directions. And yeah, I guess I don't know, but right, I'm not one of these people. I certainly agree that mathematics need not be one or the other. It's, as you say, you've identified the parts of the process that seem to correspond more clearly to our sense of what it means for something to be discovered, and which parts seem to be invented and are historically contingent, and it can certainly be both. I guess, when you ask this question, would the aliens have complex numbers, as Wigner was very, seemed to not believe in, and yet was forced to use. And I know the process by which people came up with these complex numbers. And I think maybe something that answers a lot of what you said answers his question. I think he was a physicist, and his perspective on what mathematicians did was that they were somehow just playing their own game and trying to one-up each other, and they had views, what was beautiful and what needed to be asked. And he doesn't seem to, he wrote this essay in 1962. He doesn't seem to appreciate the kind of thing that we've been talking about this whole time, which is that a lot of mathematics has developed in trying to answer specific questions about the real world that come from our experience.
It's very influenced by this. I mean,
right.
It's very influenced at the very least. I mean, even if the motivation is maybe different, it's very
right. I think it should come as much less of a surprise that mathematics is good at explaining the world, given that so much of it, we were somehow forced into it to trying to explain things that way, exactly because we were trying to figure something out initially coming from some part of experience.
But okay, so there is also, how should I phrase it? I think it's still, to be appreciated as remarkable, the fact that, complex numbers came to be when Cardano was trying to solve the third and fourth degree equations. I don't know if that was Cardano who invented the complex numbers, but
yeah, he was the one who wrote down, like, look, I can introduce a square root of -15 and it works this way.
Well, I mean, it's remarkable it came to be, and that it still, found applications way beyond the original, area of appreciation. But I would say that in all things of life, there are things that are remarkable. If you wait for long enough, some remarkable patterns emerge. So is it such a strong pattern that you can say that all kind of math that's discovered now will appear one day in some application? I don't know. I mean, the truth is that there's a lot of math, there's a lot of physics, and it's, you know, I think that's maybe the probabilists speaking, but don't you find strange patterns everywhere in the world? So then the question is how this unreasonable effectiveness of math, how unreasonable is it really from the point of from the point of view of probability? I mean, how unreasonable is it, and how much is it just not a selection bias that we capture all the things that we find to be interesting a posteriori, and we find that they are related a posteriori? I mean, at least the question deserves to be asked. Then, you know, I'm not taking sides here. I'm not saying that Wigner was wrong or right. And, you know, there are many things one can ask, but, you know, people who find interesting patterns in the world, there's a lot of them. And a lot of patterns are indeed very interesting. It's also very remarkable. You have a symbiosis between some kinds of animals. It's very remarkable that, a lot of things are very remarkable. If you know that there's a planet like the Earth at this point, and that is right in the right zone, etc. But okay, we would not be here to ask this question if it was not at the remarkable location, right? So I think one should maybe ask this question about Wigner's argument, and but yeah, I still think there are some remarkable things in the history of math in terms of discoveries that turn out to have unexpected consequences, and these are to be appreciated. But yeah, I mean, I would call for a little bit more scientific rigor in terms of making such statements. Perhaps if you make an experiment over 10,000 people, you will always have interesting, people and interesting things. And so, yeah, okay. So, I'm not taking sides there. I am just putting this in question in terms of the grand scheme of things.
Yes, yeah. I think it certainly is worth saying, we have math to describe the things that we're able to figure out.
There's that. And what do we call math? In hindsight, the math that people in 100 years will call the math of the 21st century, they will just remember a few results. And I'm ready to bet that these few results often will have connections with the real world, but that's the very reason that those results will be remembered. It's not that complex numbers, it's a bit, it's a bit different. People would still care about complex numbers if they didn't have, even if they did not find applications in quantum mechanics or other places.
Right. Well, actually, since our discussion, I just want to say, I believe from some reading, the Stern-Gerlach experiment is what absolutely forced complex numbers. You just can't.
I mean, it's true that explaining interference without complex numbers is cumbersome. It's the most natural way of doing of solving the problem. That's for sure true. But yeah. Still, I mean,
there's actually there's so many different things, in what you're saying that we could go into, because then I'd like to ask, as some people have pointed out, well, why is math not so good at why does math play a different role in biology than it does in physics or economics or history? Doesn't seem to be a lot of math in history or something. What does it?
Yeah, Asimov had this vision of psychohistory, which we are still not fulfilling, I would say. you know about Foundation?
No. I've never read anything by Asimov.
It's very nice. Yeah, so Asimov had this vision, of a very advanced mankind that would have colonized the entire galaxy. And the kind of central character in the story is a mathematician, but he's not really, he's also a psychohistorian. So he has this vision of humanity, that each individual is hard to predict, yet the behavior of trillions of individuals who are living in the galaxy collectively is fairly easy to predict, a bit like thermodynamics. So Asimov had this vision of psychohistory, that actually history is deterministic. At a certain scale, history becomes deterministic. It's an interesting view. I mean, obviously there are some parts of it that are true, in the sense that if you don't care about humans, but you just care about the future of this planet as being a body of matter in the universe, it's probably already clear where this planet will be in a million years. We don't have much choice about where the Earth will be in the galaxy in a million years. And at some level, obviously things are very deterministic about society and all that. That was the idea of Asimov. That
I see. I know.
be deterministic at a large scale.
Right.
And,
It's some, you have to look at what is there a pattern that that's at least simple to identify with what data you have that you can.
Yeah, but okay. So about other fields, it's an interesting question. I think that for fields like biology, it's largely a question of culture. That's just that if biology does not attract really, mathematically minded people as much as physics or computer science or finance.
It will not always be the case, I think.
Sorry, was not always the case?
No. I think in the future, because there will now, mathematics.
Possibly it may change, indeed. But yeah, so there was less attraction towards biology, and as a result, the field is not very rigorous in terms of treatment of things. Even in terms of experimental protocol, I think they're less rigorous than physics, for instance.
But I'm wondering if it's not. I understand this point you're making about culture. I wonder if it's something about the very objects of study themselves, and whether at a level they are at a level of complication that we're not ready for. If we're trying to talk about cell molecular structure, the shape of cells or growth, or something that you need quite a lot in order to have a useful mathematics of bio, or something. So maybe there's something so hard to describe about ecology.
No, of course. No, so you need very high tolerance for uncertainty in general in those fields. You have to accept that you won't be able to there's a lot of things that you will not be able to deal with. You have to have a very high tolerance for things you don't know, right? And that's not really the way that mathematically minded people get excited about fields. So that's going back to the question of culture, but of course that makes it even worse in terms because you need really the best and the brightest if you want to do something there. And at the same time, the field does not seem to care so much about mathematics. Okay, there are exceptions like bioinformatics and all the gene sequencing things is very, very impressive in terms of at least algorithms and things like that. It's quite impressive. But I think one ought to have mathematicians that maybe study ants or things like that. But then they would not be able to prove nice theorems, so it attracts some kind of other types of mathematicians who may be very talented. But a different kind of math is also perhaps needed. And there's a problem of supply of people, of good questions to start. Of engineering also. I think it's much harder to build things. It's much harder to build animals or things like that than it is to build molecules or to it's very hard. It's much harder to actually do like clean experiments. And the math as it came to be came from physics. In terms of and maybe economics, actually, maybe accounting and things like that. Right? Arguably, okay, so it does not, it's true that biology is way my feeling is biology is way below its potential in terms of understanding of things, but at the same time it's unfortunately it's quite obvious why, and I'm not sure this this situation may will improve necessarily.
Well, I can tell you from experience, because I've thought some of the same things and expressed those thoughts to some biologists, and they have not been too pleased. with
No, but
they
of
need.
course, there are different ways to tell people about things. No, I mean,
Yeah.
I had a very good student actually who majored initially in biology, and then he wanted to become a math teacher in high school. So he also got a degree in math, and that's how I got to meet him. And he was doing quite cool things with models of cells and so on. But these things that he did were actually for his level, like undergrad, were really, I think, very good. But again, the problem is that I like these results personally that he got, but they would not excite other mathematicians, and so because they are not like fantastic from a math viewpoint. I mean, they're just
Yeah.
the beginning of something, but they're not exciting. So you don't excite mathematicians, then biologists don't think that you're interesting. So yeah, I mean, there's a there is definitely there is definitely room for building amazing things in terms of theories coupled with kind of experiments or descriptions of biology. But yeah, I think it will first come from AI. I would say, like you will first maybe make machines that learn to interact with ant societies and things like that, and then maybe we will understand.
Right.
Understand the math of it. But yeah, I mean, the way I see the future in kind of biology is it's more through machine learning initially than through math.
It's what they're using for this this advance in protein folding. I see that as a major.
No, right. But there is that. But okay, that's more like chemistry, conceivably.
Oh, okay.
I mean, but that's the more rigorous biology. But I could imagine, I don't know, some. Have you seen 2001: Space Odyssey?
Oh, yes.
There's this obelisk that tells apes what to do, basically.
I don't know what I guess that's the message of 2001. This obelisk appears.
That's the message, right? Well, I mean, I think it's not unreasonable that we may construct some kind of robots that learn just through their interactions with the environment to manipulate animals to get to do things, but just trial and error, learning how things work, seeing how, and yeah, I mean, that may lead to a new understanding of how ecology works, etc., in the long term. But okay, that's where I would see that progress will be made before beautiful theorems in the mathematics of biology. No, the simple reason is that I think it's quite likely that we will see this kind of things fairly soon. I mean, I could envision things like that, maybe robots that manipulate ant colonies in the next decade. I mean, it's not unreasonable for me to imagine something like that. At least if there is funding, interest, and things like that. I mean, I would be very happy to do this kind of things personally.
Really?
But I think it's much easier at the point where we are. It's much easier to do that than to develop a whole theory of math for biology. Yeah. Okay, that's my take on biology.
I'm not a biologist. I'm certainly interested in these in the protein folding problem and this problem of how the brain works and understanding the role of our genes and how we are, and also growth. Those are all of interest to me. I think they should be of interest to mathematicians. You bring up something that could really be its own discussion about the sociology of what drives people into different fields and what people want to get out of something and why we put up these obstacles, I think, to smart people using their talents to study something that
indeed. But okay, and again, I think, in principle, there's room for doing math in biology. But I think we will have first advances in engineering of biology, and then advances in math, simply because there is more interest in engineering of biology. There's more funding. It's much easier to do at this point. And that seems like the first, the next thing in terms of, it seems like it's much less of a long shot, actually, than the math of biology. So as a result, I think that's how things are going to happen. I'm not saying that this is how things, would have had to happen anyway, but this is how things are going to happen. That's what I believe. And because, okay, biology being what it is, and I'm not seeing this changing in the next 10 years somehow drastically in terms of how interesting it is to mathematicians, so on and so forth. And because we will have major advances due to machine learning in that field, I think that's how things are going to be here. But I may be wrong, but but it would have been very different. A different, history could have led to different results about that. That's what I mean.
I want to ask you one more topic, one more question, I guess, that I feel like I have to get to. What is your view? And maybe you don't have any view. I don't know. What is your view of these so-called fundamental theories of physics, or maybe there's a fundamental theory of math? There are people out there who seem to think that they could unify, that there will be someday a total understanding, or at least they put forward some issue at the foundation that could explain it all. And that would be maybe the most natural.
Absolutely, no, 100%. That's the most natural question ever. How
I
do
see,
you
I don't know if you follow the I don't know, because I see him on YouTube, this guy Eric Weinstein. And there are other people who have other people with their fundamental theories. What do you think about the prospects of any of that, or whether there's any kind of fundamental? There are people who really think there's a unified theory of math out there, maybe around the Langlands program or something. Or
yeah, okay. About the people themselves, usually I'm
no, not about the people themselves.
Yeah, okay. Because I could say something about the people. Okay, I could say something about the people, but putting all of them in a single bag and not being too specific about. I think to me it sounds strange that you have a big theory that solves everything, yet you cannot solve anything in particular. That's the kind of yeah, okay. Yeah. But I would like to see someone who has a theory of everything. Actually, just teach me basic quantum mechanics in a good way. Already, that would be encouraging, I think.
Yeah, and yet it's
that being said, about the question, and okay, also we could focus on string theory as okay, maybe that's also a topic for a different discussion. But I really like string theory, and I think it's I can at least for string theory I can see why people thought that is all that was. That's the thought there is really a path towards a unified theory. I mean, like it was not just people bullshitting themselves. I mean, there was really a reason why people went that direction. But okay, anyway, so is that an interesting question? Yeah, I think it's definitely a very interesting question. I mean, as you said, one of the most natural ones. One should be very careful still about. I think that to some extent, one should still have a epistemological view of this in terms of complexity of explanation. I mean, so basically, you claim to have a theory for everything. So how long is the explanation for anything in your theory? Somehow, what is exactly the you claim to be compressing information. If you build a unified theory of something, you claim to be compressing the information of lots of theories into a single thing. So just be careful that this single thing is not bigger than all the theories that you're actually compressing information, right? And that you're compressing the information, and not at the expense of, not at an unreasonable expense of computation. If I have a file on my computer, I compress it. Maybe there are some formats that I can, that compress just a little bit better, but that cost 100 times more in terms of decompression time. So there's really that question. So actually, so just are you sure that your theory is actually smaller? Are you sure that your theory actually explains everything? And things like that. So it's still so in some sense it's an optimization problem. Okay, that's not really the correct way to think about it. When you try to discover a unified theory, I want to compress things. No, I want to, I think the correct way to think about this is, I really want to explore something, because this problem is too complex to attack from an optimization angle. But okay, one should still, once the theory claims to be there, one should still ask that question very much, right? So the way physicists do it is a way that I think is not very satisfactory. They say, provide me an experiment that is not explained by any other theory, a new experiment to do that is not explained by any of the existing theories, and that will be the benchmark. But I think it's a very,
But you don't like that test?
It's
I think
very
that's
contingent on many things, and so what if you cannot make new experiments? What if you don't get funding for your next
that tells me
accelerator,
that
right?
would tell me don't be, that's not the important question to be asking right now. If that's
Yeah. So somehow, I mean, I think that that used to be the benchmark for physics, and I think it was a pretty crappy benchmark that still led to the correct thing eventually. And so it was like, historically it was a good benchmark, but I think it was an accident that it was a good benchmark. There's no fundamental thing about you being able to build an experiment. I think that's really well, that's an epistemological mistake, I think, at the heart of physics. But at the same time, it's true that if you're able to predict something that's not been explained before and that's not been observed before, yet you predict it, it's a strong sign. It's very heavily correlated with the fact that you have indeed successfully unified your theory. And of course, it's a good narrative also. And that's also much more important than people acknowledge in science. You get a good narrative. If you discover, antiparticles, after playing with equations like Dirac did, of course, that's a very, very strong narrative. Yeah. But I think the wiser question to ask is, okay, how much are you helping others, right? How much are you helping? With your unified theory, what are you really providing? What is your added value?
That goes to that thing you said, solving problems.
Sorry?
That goes to what you said about solving problems, which I think is the real test. Boy, you say a lot of things here that one, I might challenge people as to whether there should be at rock bottom a fundamental theory, period. How do you know that you're ever going to have it all?
Okay, so I would say this, perhaps what we would want is to, but that's a very computer-centric vision, but it's still, I think valuable. What one could want is to be able to kind of run a simulation of the universe at kind of, putting, a simulation, a single program where you can put inputs about your initial conditions, the setup of your experiment, and it can spit you out the best possible answer that is available to mankind at the moment. So that computer program, okay, so if it is a neural network with quintillion parameters, then you will not be happy. You will say that's not an explanation of life, and probably there are some experiments that it doesn't predict very well. So you want to compress that information. So I think ultimately that's what unified theory should aim to do. It's to be a fairly short. It doesn't need to be that, but to imply that one can write a fairly short computer program such that, given enough compute power and memory, and given some initial condition, can predict the future at various scales. So I think one could ask for this.
That is one test. That seems to me to actually be a pretty high bar.
It's a high bar. It's a high bar. Yeah.
I mean, because why? There's so many things here. Why think, first of all, that everything? One, why think that there is some total explanation of all things? Two, why think that it's important even to unify what knowledge we have? It's sort of along the lines of what you're saying. Maybe that explanation is too big, is not efficient. But also another issue could be, well, if you're already are able to answer the particular you know, maybe you use different mathematics and different physics when you're talking about something at the scale of building a car versus something at the photon or whatever.
Yeah, but obviously there's an unsatisfactory thing about a crossover. I mean, you know, I mean that much is obvious, that it's not very satisfactory. If you need one theory for one scale and one theory for another scale, okay,
Yeah,
where do you stop
doesn't please
using?
people. It doesn't please people, but if it does the work that we want.
No, but you know, I think, you know, I agree somehow in principle. If one comes up with a kind of yeah, I mean, I see what
Okay,
you
so
mean.
suppose you did that, right? So now, what is the value? Suppose you synthesized, I don't know, all of our knowledge,
Yeah.
and you have this language that can do it. Is that what we're asking for? Because my test would be, I'm not satisfied by that unless that helps us to answer questions that we couldn't answer before. Because if we really are able to do it with what we have,
then you would be a person who would be happy with the neural network that predicts basically anything about an experiment you can propose. And you know, I think we will have neural networks that can do that at some point. Not very soon, but at some point we will have that.
I wonder.
But you know, I think there is the question is, you know, I mean, there's this question which is completely different question, which we have not touched upon, and which is related to this future paper I've told you of this channel about, which is proofs. You know, okay, so if you have a proof that is a terabyte in length, are you happy with it? You know, I mean, it depends. I mean, are you happy with the proof of the four-color theorem, for instance? It depends.
I'm perfectly.
You're perfectly happy with it. No, I'm not perfectly happy with it in the sense that I cannot explain to a friend why the four-color theorem is true. And if there was a kind of nice proof, like the five-color theorem, I mean, that you,
Yeah, but I think
then I would be happier. Okay.
I see. I think it works way.
Again, it depends. It depends what you want. It depends what you do math for. It depends what you do physics for. And I think, you know, I would not deny the value in having a simple theory that explains everything. It would have a value, and just for humans, a value for other humans, something that you would teach once and for all that would just encompass everything. I think it would have a value. Maybe there is too much value put on that, but it would definitely have a value. One can argue, and I think, you know, in some sense, there is too much value put on that, because the very reason that many people come with bullshit theories of everything is because there is a prestige associated with that question. Yeah. You know, people don't come up with, you know, with bullshit solutions to an Ising model correlation question, because just there is not enough hype around that. And maybe that's good for the Ising model correlations, you know, that there is, but, you know, people tend to gravitate around some kind of vague questions where they feel they can bullshit their way, you know, and where they also feel they can, you know, claim they have prestige. And so maybe there's too much prestige attached to that question. But when one has to understand why there was a lot of prestige, it's obvious why. Because whenever a successful unification was done in the past, it led to new discoveries. And yeah, I mean, that's history speaking for that that thing. But, you know, I think independently of the new discoveries, there's definitely, you know, value in finding simple.
Do you think that that's happened in math?
What simple, you know, unifying theories in math. Okay, so that's I think it's a bit different here. Unifying theories in math, in a sense, I don't see why they would be needed. But unification of math still, there was some that happened in the beginning of the 20th century. I mean, I mean, this formalization of the axioms, I mean, as boring as it is, I think it did really provide, at least, it clarified the fact that, you know, math somehow was, geometry was somehow the same kind of topic still as analysis and allowed perhaps later for interactions between these fields. I don't know, but
I guess I'm thinking of the example of people like Weil and Grothendieck. Didn't you mentioned Grothendieck first in this discussion?
yeah, I said there's no on the alien planet. There's no guy
There's no
named Alexander
Grothendieck. If there's
Grothendieck.
no Grothendieck, things might be very different. I mean, here's a guy who really believed in a conceiving of the correct mathematics.
Yeah.
Right, and finding the most natural, the right language, a language that
would trivialize everything. Yeah.
Exactly. And he and Weil, you know, in trying to answer these Weil conjectures, they thought, well, we will unify mathematics along with topology, so that there's topology not just for Rn or, you know, Riemann surfaces. It's also for number theory. It's also for arithmetic geometry over finite fields, right? And they, you know, they need the right cohomology theory, and they reworked a lot of mathematics, right, to provide this language. And I think so many students, they learn, you know, the way algebra is taught today and the way a lot of things are taught has some of that philosophy in it.
Absolutely. Yeah. I mean, it's not my way.
And it's not clear to me that it really did the thing that they hoped that it would. I mean, people were able to prove these things. You know, Hasse, there are analytic proofs of what they did, and Dwork was able to prove the rationality of this zeta function without all their topology. He did it with analysis, and I guess I don't really understand Deligne's proof, but I gather that he didn't do it in quite the way the philosophy was supposed to answer the question. Right, and I wonder.
Good question. No, good question. So about the unification of math, then, yeah, I mean, I think it's, you know, it's something that could have had value, but was a project. I would say, okay, that's maybe harsh of me to say, but ultimately it didn't work, in the sense that I'm not saying it's not possible to unify math, but I've yet to see a successful attempt at this. And then, you know, there was this thing that somehow worked in its specific niche, and that was pushed very hard by people who just believed religiously in this fact that this was the right way to do it. And you know, and if you just don't have the right way to do something, then you can push as hard as you want, and you will not. It will not be a success. And I think it was not a success, and I've not seen other, you know, I have not seen other attempts being successful either. That said, I could imagine that if, you know, one day someone would come up with something that is actually helpful. But yeah, for math,
come up with things that are helpful.
Yeah, for math, it's I see less of a demand for unification than for
there are its proponents for certain. I guess there's different. Maybe we should parse out. There's one aspect of this, which is that there are people who want the fundamental or the total or correct answer. You know, this guy Eric Weinstein talks about trying to learn the universe's source code. That to me tells me he wants like the totality, the whole thing, what's really at rock bottom. Then there's this other issue, I guess we're talking about here, about finding a framework to which to unify things that we already know, and hopefully, you know, and then there are people who really elevate that and think that if we had that we'd be closer to the fundamental thing, as though that were what is fundamental. And I guess I'm skeptical of both of these.
No, I understand you. You should be people should be much more skeptical than they are in general. It's good you're skeptical. I think, you know, grad students and you know, are not skeptical at all about things in general, and that's bad. But okay, anyway, they're you know, especially grad students in math, they're very they believe everything they're being told. That's my impression. Yeah, okay, anyway, so just about physics, there's still this idea that, you know, there are different scales, and scales should be related one another, and that's, you can phrase it, you know, it sounds like a natural problem, and that all these unified theories, they in principle should also aim at solving that problem, explain how one scale is related to another, in particular, or get something at one scale and reduce and get the next scales as a result. I think it's fairly natural question. Math, it branches in a lot of directions. And what do you want to unify exactly? So, what do you want to explain analysis in terms of algebra? What exactly do you aim at doing, right? Or do you want maybe just a program that can find all the theorems for you? Maybe that's what you want. I don't know what people want, right? They've not made it very clear anyway. I mean, even Grothendieck and people like that, they have not made it very clear what they wanted. Short of clarity in terms of what the question really is in terms of unifying math, I'm skeptical as well. Right? I mean, the question may very well be, find me a 1,000 line code in some language that reproduces the math that was done, until 2021. If being asked the right questions, right? I mean, it could very well be that question, but that was not the question that Grothendieck tried to ask. And I'm not saying that this question I just said is a good one either. But, to me, it's not very clear what natural meant. For me, it meant more like they did something and they had some kind of sense of something, but they never made it explicit enough. So one can discuss really that this was a good idea. I mean, they never, for instance, took into account simplicity. They never defined simplicity. They never defined complexity of proofs and things like that, which were, by the way, things that were defined by other people, which those people like Grothendieck completely ignored, like Solomonoff and people like that. They really studied the complexity of description of things in terms of Turing machines and things like that. But those people in algebraic geometry type, Grothendieck type, they never cared about those things. They are very proud never to, care about anything very concretely. But in the end, so they claim to have the best theory without ever caring about benchmarks. What is a benchmark? What is an optimization problem? And to me, that sounds extremely fishy, But yeah.
I see. So you've actually added, you said a couple of things here. Yeah, what is the value of some synthesis if it's somehow more complicated? Whereas, I guess I'm thinking both of, the merit of any new physics or math, anything that you're saying is the ability to solve problems that you couldn't solve before. And I'm a little bit confused, I guess, exactly why you were rejecting. It sounds like you were rejecting experiment as the benchmark, because I know in the history of physics, it has only been when there have been these crises, when something that you now think you're able to measure doesn't come out the way your theory predicts, and it forces you to do something. That has been the way that things have developed.
But assume you're a theoretician. It means basically, but okay, so there's this question, right? I mean, did quantum mechanics really need the crisis of the end of the 19th century to emerge? I mean, it's a real.
Otherwise,
I mean, if you were a theoretician back in I don't know 1880. Could you not have done a better job? I mean, it's a real question, because at the moment there's this thing that there's maybe no experiment, but okay, maybe one thing to do is just to say, well, we shut down all the theoretical physics departments until we have a new experiment. Another option is just to ask yourself the question, okay, maybe look back in those days. Maybe if they had asked the right questions, they would have gotten the right answers before being pushed there by the experiments. I mean,
I don't think I think that's a very interesting question. Could someone have anticipated quantum mechanics without the ultraviolet catastrophe and the Young slit experiment and the Stern-Gerlach experiment and the photoelectric effect?
I mean, one can ask this question. I mean, okay, special relativity, it's much easier to answer that yes, resounding yes.
Yeah.
Okay, quantum mechanics is
people should have looked at Maxwell's equations and said, what symmetry group,
Exactly. So it's a resounding yes. For instance, okay, a question that I loved when that got me very intrigued.
Can I just say, but without the experiment that measured the speed of light in different directions, with Michelson-Morley and so.
No, I mean, okay. So of course one needs some experiments, but what you're saying is in terms of explaining new experiments, it's currently now, what is the best thing we can do? Is it to stop doing theoretical physics, or is it to just still try to think, what should we do now?
Yeah,
Right?
I actually do think that theoretical physics is in a completely is in a terrible place, and they do need some reorientation for.
I mean, okay, perhaps, etc. But I don't think the question of unification is devoid of merit in the absence of further experiments. But okay, so that's my thing. My take. I mean, what I mean, of course, these people who claim to have these unified theories, most of the time it's just vacuous language, and there's a lot of things that are worth clarifying. Also, just string theory. Of course, there are problems that are too hard to really tackle, but still, it would be good to spend time clarifying things. Okay, so you have to what extent do you expect that one can, in principle, one can compute scattering amplitudes for particles from the principles of string theory? I mean, to what extent is it possible? How much computation power would be needed to do that, etc.? I mean, these are questions that I think should be more discussed. But okay, anyway. So, but you said something else. So what were you saying? So yeah, I mean, I was about to tell you a story about something that I really liked, because it's something in my life that I didn't know, and then I knew, and I was very happy when I knew.
Good.
It's there's a law of refraction, Snell or Descartes, depending on whether you grew up in an English or French-speaking country, I guess. And so I think it was Fermat who observed that it was as if the light was trying to find the shortest path,
right?
I mean, in terms of time, right?
Have you seen, by the way, there's a great story. This is the only thing my calculus class liked that I told them, which is that same thing will happen with ants. Just to go back to our biology, if you put like a hardwood floor here and like Velcro, that's harder for them to walk on, and you put their food at one corner and they start here, they will make the ants will follow Snell's law based on.
I mean, okay, not the first time, but eventually they will optimize the project.
They will settle on that path.
No, but of course. But okay, so from that could be a coincidence, or could be not a coincidence. And if you're a 19th century, physicist, and you don't believe in coincidence, you believe that there's a deeper reason for this. You start being, puzzled. How does the light know which path to take, right? Because ants, I mean, it's clear what happens. I mean, first they don't take the right path, and then they optimize the path. But light seems to just go straight, and basically the answer came with Feynman. Actually, I believe that it was Feynman who was the first to really clarify this. And one way to explain this is with the path integral, and to say very loosely speaking that light takes all the possible paths, but eventually the complex amplitudes cancel around, except around the minimum of the length of the time length, and so that's how you get that there. And basically it's very deep, right? Because you start from a simple observation, then you realize there is a minimum action principle, a least action principle. And then maybe you realize that all of nature follows least action principles, and then you wonder, how is it possible on Earth that nature follows least action principles? And you could possibly then you arrive to quantum mechanics, actually, through the path integral way, and that's a completely different.
Wait. I disagree. Just because I feel like people had solved this, brachistochrone problem, and they had studied the calculus of variations before, and Feynman's answer is sort of an answer which addresses that. At the same time, it's also thinking about quantum mechanics and probability, and it's like it solves the quantized problem where every path is given a weight.
That's right. But if you have that, then you have quantum mechanics, right? And you don't need all the operator. I mean, I mean, it's not that you don't need all the operator algebra and so on, but it can be derived from that formulation. That's one of the formulations of quantum mechanics. So what I mean is that if you are a theoretician, a crazy theoretician of the 19th century, and you ask the right question, you can arrive to the path integral formulation of quantum mechanics. Obviously, people are going to think you're crazy, but you know, you may get the right answer. So similarly, you know, we can be now in the 21st century, early 21st century. Okay, we don't have a crisis in terms of experiments because maybe we have a crisis in terms of funding the experiments. But you know, there's a yeah. Okay, we don't have a crisis in terms of experiments. Well, can we still be smart? I mean, I think it's worth asking this question.
It's actually it's a very interesting question, but I actually think, you know, when I said I'm skeptical, I just want to make clear I am skeptical both of the particular claims of fundamental theories, but I'm also skeptical of the philosophical project.
I got that. I got that.
And I just and the reason why is exactly for the kind of thing that we're talking about now, which is that the way that progress is actually made, when I look at history, is this historically contingent process, always of you can only answer the you know, the questions that are in front of your face somehow. It's only what you can think about, what you're interested in, what you can measure, what with the current.
I agree. One should be humble. One should be very humble, and one should not think that what is able just through the power of one's mind, just to discover you know, big truths about the universe. That's really the way it works. I mean, the examples where it worked, and you know, I think perhaps like Dirac was the most emblematic example of a guy who just, you know, stare at his fire.
I think he was very lucky. I think he was very lucky that his equation explained something, you know, that they found.
Yeah, and who was extremely lucky, and maybe that was a bit damaging to the culture of physics. Perhaps that, you know, people started thinking that they can all be like Dirac.
Yeah, and I think in Einstein's case, he was answering questions that had sort of lingered and could have been answered if people had looked at them before. It certainly.
Yeah, I mean, Einstein's discoveries, you know, came in a moment where, you know, they were very much in the air of time, of his time. I mean, you know, it's of course very hard to remake history, but it's fairly clear that his ideas would have been discovered within 5 years by someone else had he not published them at the time he did. At least for special relativity and general relativity. I mean, Hilbert had the Hilbert-Einstein equation. Yeah, I mean, Hilbert was maybe not as good at understanding the implications of, you know, physical implications of, you know, an equation like that. And, you know, Einstein had the right point of view, the right, you know, many things, but still, it's true. You're right. It was much more in the air of time, maybe, than the idea that Dirac had using quaternions.
Well, and I think people have taken the wrong lesson where they all tried Einstein, and that's not how one should do.
But you know, I think it all depends on the people and so on. I mean, I think maybe you're closer to those people in string theory, or who really wanted these fundamental truths and all that. And maybe you only see them. I think there's, you know, first, there's a small minority. It's true that it tends to attract the best and brightest for various reasons, right? Also because the math is much more interesting there than the math elsewhere. Yeah, that's not negligible as a factor.
There is some good math in string theory. I'll give it that.
Yeah, it's much nicer than the math of, I don't know, plasma. I mean, even though plasma is very interesting.
Hard. You're combining Navier-Stokes with Maxwell's equations, and suddenly.
But still, it's not. I mean, yeah. I mean, it's you know, I'm sure it's nice from a PD viewpoint, but
why think that the string theory? Why think that is better? I mean, here you have a hard problem. To me, it's whatever, you know, problem is somehow amenable. You know, has rigidity enough to be able to say something, but flexibility, that there's complicated behavior, and amenable to your tools so that you can.
Yeah, but okay, as of 2021, I think the math of string theory is still much more interesting than the math of plasma physics. I mean, for my standards, right? But it depends really on one's standard. And conceivably, if there were more brighter minds going to plasma physics, first we would have nuclear fusion, and second, I mean, like commercially available commercial nuclear fusion, and perhaps we would also have very beautiful math of plasma physics. But conceivably this, but okay, there's a network effect and all that. But I think okay, what did I want to say about this thing about fundamental truths? Okay, so one could make the case that it's not worth pursuing unification. I still think that it's quite. I mean, again, I don't think it's necessarily the case one has to pursue unification, but I can understand, given the history of the topic, given given how string theory came to be also, then one feels, at least one could feel at some point, that one was very, very close to having something very, very nice. At least, okay, I was not one of the people who worked in string theory when it was developed, but if you read courses in string theories and lecture notes in string theories, and you see these things, a bit, maybe the history was rewritten in those lecture notes that I read, but still I read them, and it sounds really that nature is sending you a message. I mean, not nature, but math is sending you a message. Oh, you should go there. You should go there. There is definitely something interesting happening there. And then you can argue that the way in the end it was done is still not right, in the sense that people all had big ego. I mean, not many of these people in those fields had big ego, no humility, no real desire to actually explain something concrete. You could argue that, right? There was a culture problem. But I think the whole question is not irrelevant, and and then there are many interesting results that came out of this. And I mean, it's a bit under fire for various reasons, but yeah, I think it's much more interesting than most of math, actually, string theory as an activity. It's closer to experiments still than most of math, and it's deeper in terms of intellectual depth. Okay, something that we can discuss a little bit another time, perhaps, than most fields. It's more natural in many ways than most fields of math. And there are more interesting conjectures and problems to be solved than most of math. So in terms of being interesting, I think it's very interesting.
Certainly from a mathematical perspective, I guess the mathematics that I did, did touch what I guess is part of string theory in some way, and these there's a lot of interesting problems about canonical metrics in algebraic geometry and moduli spaces.
But maybe people were too attracted by those problems. It's true that there's maybe I think a lot of people in string theory pride themselves in not doing anything useful, and I think there's a cultural problem in just like string theory. There's definitely a cultural problem, but the very question I would not dismiss outright, personally. I mean, I understand you dismiss kind of the very pursuits outright. I would not dismiss it outright. I think there are problems, but the whole thing, personally, I think it's.
Are you at all familiar with the work of Thomas S. Kuhn?
Absolutely not. Never heard of this guy. The
Structure of Scientific Revolutions?
No, never heard of it.
Oh, this is a fantastic book. It changed my view of science and what we can know. You should go out and read this book, right now. Someone told me I had to do it before he would continue discussing something with me. And he's a very, I think, misunderstood guy, or maybe later in life he got too into postmodernism or something, and is interpreted by people as saying sometimes that there's no such thing as truth in science, and I don't think that's quite what he was saying. But he described in this fantastic book, The Structure of Scientific Revolutions, the process by which science actually happens, and he described there are periods of normal science where people work within some conception of the world and their set of concerns and what they can measure and talk to each other. And eventually it fails. Eventually it reaches a crisis that is resolved by a new theory, and a new paradigm takes over. He introduced that term, paradigm. And I guess maybe it is my thinking, based on his, I think, very good analysis of how science has actually proceeded in history, that the people searching for fundamental theories are failing to grapple with, because you know, that's not what's being asked for, or even that you could ask for right now, or possibly even ever. All you can really do ever is look at the problem which is in front of you, the things that are accessible.
I kind of agree with that. I mean, short term is completely underrated in you know, in math, for instance. I mean, I'm speaking of math because I know the field much better. I mean, people always say, yeah, maybe in 100 years it would be useful, but yeah, I think there's you know, I think short term often wins in terms of, you know, but clear progress in terms of yeah, in terms of eventual impact and things like that. But okay, I would say that though, I think short term is underrated in the academic world in terms of, you know, like doing things, etc. It's a bit underrated. In the rest of the world, it's completely overrated. Short term is the only thing that matters in the non-academic world. You know, short term is the only thing that matters, and long term is completely disregarded, and so that's also a catastrophe. So I think it's a problem specific to academia, that people think too, you know, because it's a polarization effect, right? The people who don't want to think short term, they go to academia. The people who want to think short term, they go to the real world, and there's a polarization effect, and you know, it's not good. But I think you know, I don't think that short-term like thinking is the right way of thinking in general, but a shorter term way of thinking within like sciences like math or theoretical physics. Yeah, I think, you know, here it may make sense. You know, I think people should, you know, string theory should focus much more on doing simulations of string theory to the extent that's possible, and doing like practical things, that, you know, things that where they can show pictures and so on. I think that, you know, people in math, they should spend a lot more time doing like kind of easy things in some sense, like simplifying proofs, like getting nice arguments and things like that. Yeah, okay, then that's not exactly like the problem in front of you, but in general, people should, yeah, just not be, I mean, there's a problem of smart people being way too grandiose in their expectations, and that's not good. But I think, again, that's a problem. The reason it's a problem is because there is such a focus on abstract things in certain fields that, you know, one needs to bring them more concrete. But the rest of the world is way too concrete, I think, in their thinking. You know, most people just think paycheck from paycheck, and, you know, most companies think quarter from quarter, and there's no long-term thinking, and it's also very, very bad. You know, yeah. Okay.
I see. Okay. I guess I wasn't trying to say there should be no long-term thinking. I need people to invest in, you know, a project of mine that may take a couple of years before it works.
Yeah, no, what I'm thinking more, you know, it's something, you know, for instance, I mean, one reason I got very good at some things in probability and so on is just because I played, you know, making simulations of various things, even things that was not asked. Why did I do that? Not to write my paper, just because I had fun doing that, and because I thought it was nice, and, you know, I got nice pictures. And because of that, I got much stronger at solving some problems that, you know, people who just claim to be like pure thinkers and whatever, they just would not be able to do that. And that's what I mean. You know, people should think more about, you know, kind of concrete little silly things. It's also written actually in Feynman's book. You know, he explains that, you know, at some point he's at Cornell and he's like just playing with plates that spin around sticks, and he's just trying to compute the equations for that. And then there's a professor who asks, yeah, but what's the point for this? You know, why are you playing with plates and sticks. And it's just, yeah, just I like it. I think it's nice. It's a nice problem. And he actually says, a few years later, he was, it's the same kind of calculations he was doing that led to the Feynman diagrams that led to, big discoveries. And, I think people should be, should not be too, again, they should not say, I'm just working on this grandiose thing. They should just do what they can, progress, make sure that every day a bit smarter than they were the day before, and things like that. Make sure they are also helping their colleagues to get a bit better than they were before, and teaching something to each other, learning something every day, and not learn something because they read that it's the latest fancy thing, just because they actually like it, they think it's nice. And I think if there was more of this kind of thinking in many very abstract fields, there would be much more progress. But again, the rest of the world is very much the opposite. Outside of academia, people just think, yeah, okay, if you're a trader, you just think what's going to happen in the next millisecond. But okay, that's very, very short term. But the rest of the world is crazy in terms of narrow-mindedness and just looking at very concrete problems. So it depends where you are, whether this is a problem or not.
No, this is fair. I think certainly what you're saying speaks to the fact that this is a process. The way that we come to learn things. I mean, you're talking about the way, if you pursue your interests and the things that are in front of you, you'll get to the next step. You'll make that progress. And I think whatever we say about these aliens with their different math, if we still believe in that evolution, they will. Whatever they are, they come to it via a similar process, different environment, different, different kind of intelligence, perhaps, but same process. And I'd be willing to bet. Here's my hypothesis. You encounter those aliens, they're going to have whatever math they came through with that process. They're not going to have the source code. They're not going to have the fundamental theory. They're going to have a version of knowledge that was able to allow them to travel or whatever. But they know up to what they know and no more, just like us. That's my.
Yeah, I mean, what the case one could make for against fundamental physics is that maybe it's a bit early for unifying things. And actually, basically, the fact that one has not succeeded yet in unifying things is a sign in hindsight it was a bit early.
Well, I wonder if, I guess what I'm saying, if I believe Thomas S. Kuhn, and there's always another paradigm, you can only probe so far. You'll always have a model. You'll always have a model that is capable of explaining everything in the past and predicting, the results of experiments that are accessible to you now. And there's never any reason to think that it will be the totality, that it will somehow always work when you want to probe, and now when you want to compare it against some other thing in the future, when your concern is different or at a different scale.
Actually, okay, maybe it's a bad idea to switch into politics, but it's a very communist way of thinking of.
Wait.
I mean, this no, not you. No, this kind of idea that one should do a fundamental theory and something like that. It's a fairly communist way of thinking of science, and maybe the more libertarian way would be to think, yeah, well, everyone does what they can, they solve their problem, and together it will just create a nicer science. I mean, there may be some political, side to this question.
I don't know.
I think based on the kind of people I've met in very fundamental things like algebraic geometry or string theory and so on. Maybe there's really a correlation between political ideas.
Grothendieck had some very extreme.
Yeah, obviously Grothendieck, but also people of our age, just in those fields.
Oh, people my age. Well, look, I think we covered a lot here, and there's so much more. I don't know. You can work on your theory of the politics and theories of organization of math and physics. I'm sure we'll return to these ideas again, because
well, I need time, I don't know how many times you will bear with me on this channel, but I'm always happy to come to see you.
It's a lot of fun.
Yeah. Okay. Good night.
Okay. Thanks a lot.
Bye.
All right. Bye.